Hi, today class we will talk about source channel drain energy band diagram, and second, MOSFET mobility, and third, enhancement mode and the depletion mode. Last week we talked about the MOSFET energy band diagram and the IDVD curve and the IDVG curve. So, and as we talk about the MOSFET energy band diagram, we always talk about the cross-section view of the MOSFET. So the cross-section view of the MOSFET will be the no so the source channel drain energy band diagram will be the cross-section view of the MOSFET, and before we talked about the MOSFET energy band diagram was the metal oxide semiconductor. So we will talk about the source channel drain energy band diagram. So for example, we will use the P substrate and the NMOS. So the energy band diagram will be like this, and this part will be the Fermi level. So we use N plus polysilicon on the metal side, so the Fermi level will be very close to the conduction band, and the channel part will be the P substrate. No, the N N type N type semiconductor. So this part will be at like inversion or depletion part. But I think this part will be some kind of inversion, but yet this will be not yet a strong inversion. So let's draw some Boltzmann tail on it. So we can draw the Boltzmann tail like this. So in this energy band diagram, there are none of current are flowing. So actually, there are some kind of current flowing because in this part, this part of the this portion of the Boltzmann tail, so the electrons can go over the channel, but the net charge will be net current will be zero because this part will be uh, go over to the channel. So the source to channel and the drain to channel, the sum of the source to channel and the drain to channel will be the same. So the net charge will be zero. So we say there are none of current flowing. So if we have some gate bias on it here, VG, so let's have some positive bias on the gate bias, and the channel's barrier will be goes lower because when we have some plus bias on the energy band diagram, the energy band diagrams goes lower, and when we have some negative bias on the energy band diagram, the energy band diagram will goes up. So the portion of the electrons can now go very easily to the channel, but yet the current is not flowing not yet because as I mentioned, the net charge will be zero because the same amount of the electrons will go over to the channel in source to channel and the drain to channel, so net charge will be zero. But if you have some, here will be the source, and here will be the drain, and here is source, and here will be the drain. So when you have some drain on the drain bias on it, and the bias will be the positive. So as I mentioned, when we have some positive plus bias on the energy band diagram, and the energy band diagram will be go slower. So the energy band diagram will be like this. So and there now the current can goes flows over because the source part of the this Boltzmann tail will go to the drain. But on the drain, there are none of electrons can go over to the channel, so go to the source because the amount of the barrier will the 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 amount of the barrier will be very high to the drain electrons, so the drain's carrier. So there are some kind of carrier transport on the source to drain, but not to drain to source. So, so this is the NMOS. So the electrons move to source to drain, but the current direction will be the opposite to the electrons direction. So the current will flow drain to source. So this was the source channel and the drain energy band diagram. So it is not different to what as I mentioned before. So we have to have some gate bias to because we have to low down the low down the barrier. So the Boltzmann tail will have some less barrier. There will feel the less barrier on the sides, but when we have none of when we have none of drain bias on the MOSFET, there will the net charge will be zero. So we have some drain bias on the MOSFET, so the energy band diagram will be bent, so the current can flow to drain to source in NMOS. So the PMOS will be the opposite. So we have some gate bias on we have some minus bias on the gate side, and the drain side will have some minus bias, or when we have some ground on the drain, the source will be some plus bias on it, so the source will be goes lower, or the drain side will be goes upper. So the holes will go to source to drain, but the hole's direction will be same to the current direction, so the current can goes flow to source to drain. So this class is for the this class is semiconductor engineering, but in microelectric circuit, we have some symbol like this, and this arrow will be the source, and this part will be the drain, and this part will be the gate. So the source, the arrow's direction is going out to the source. So this will be the NMOS, and this will be the gate, the source drain, and the current flows into the source. So this will be the PMOS. So this was some kind of symbol of the MOSFET. And next we'll talk about the MOSFET mobility. So uh, there are many kind of many kind of things happen uh, on the MOSFET. So when the electrons moves, there are some kind of Coulomb scattering or the lattice scattering. So the scattering will low down the mobility. So like when there are some kind of ions on it, fixed ions, the electrons or the ions can go like this and like this. So this kind of Coulomb scattering will low down the mobility. And there are some kind of question about why the mobility is important on the MOSFET. So let's have some let's let's remember some kind of current formula we had we had learned about last week. So in linear region, ID will be the W over L mu C ox and the VGS minus VT and VD. So the mobility will be some kind of we have in when we draw the ID-VD curve or the ID-VG curve, we had have some hypothesis. We assume that the L and the W and the mu and the Cox will be the constant, but actually the mobility can be changed. So if the mobility goes de the mobility decrease, as I mentioned, like some kind of lattice scattering or the Coulomb scattering. So the when the mobility goes down, so goes lower, ID will be lower if the VD will be the constant. So in the ID VD curve, if the mobility is lower, it will be drawn like this. But same threshold voltage and the this will be the mu and this will be the mu. So this will be the higher mobility and this will be the lower mobility. So we if you have some same voltage on the MOSFET, when the mobility will when there are some higher mobility, there will have some higher the bigger current flowing on the MOSFET. So this will have some have some uh, and so this is the important thing on the MOSFET. So finally we will talk about the enhanced mode and the depletion mode. So as we draw the IDVG curve on it, uh, VG and ID. So this will be the threshold voltage, but this curve was the enhancement mode. So in zero bias, there are none of current flowing, and when we have some bias on the gate side, and if there are some drain bias on the MOSFET, so and the gate bias is over when the gate bias is over the threshold voltage and there are current flowing, this is the enhancement mode. So the standard will be on the zero bias. But the depletion mode are some kind of the depletion mode of the IDVG curve will looks like this. And this will be the threshold voltage, and this will be the zero bias. So in the enhancement mode, there are none of current flowing in the zero bias, but in depletion mode, there are current flowing at the zero bias. And when we have some threshold voltage on the negative side, the current are not flowing now. So this will be the depletion mode, and this IDV curve is for NMOS, and for PMOS, the VG and ID. So this will be the PMOS enhancement mode, and the it'll it'll look like this. So actually, it is same to the NMOS. So the on the PMOS depletion mode, the zero bias, there are some current flowing. So this was the enhancement mode and the depletion mode on the MOSFET. So um, this class will be the final video of the MOSFET. So the next video will be the short channel effect or the capacitance of the MOSFET. But um, the basic picture of the MOSFET will finish by this video. So thank you for watching my video. So yes.